This is a brief lecture to introduce you to the concepts of abstract classes and interfaces. So let's jump right into it. What is an abstract class? Well, an abstract class is a mouthful in terms of the definition we've got sitting in front of us. A class that represents a generalization and provides functionality, but is only intended to be extended and not instantiated. That's a big run-on sentence that basically tells you that an abstract class, the entire purpose and existence of an abstract class is to be extended by other classes. It's meant to be a superclass, and other classes are then meant to inherit from that class and take on its functionality or extend that functionality as they see fit. So what's really nice about abstract classes is that it lets us define a generalization that can then be shared amongst a number of specializations or specific concrete implementations of classes. And a couple other things that we'll talk about as we go through this, but really the key takeaway here is abstract classes are meant to be extended and they can never ever be instantiated. So let's talk a little bit about abstract classes and how they differ from regular classes. First of all, an abstract class may contain instance or static variables. There's no difference from regular classes in that aspect. Abstract classes may also contain instance or static methods. That's no different than regular classes. Here's where things start to get a little bit different. Since an abstract class is only meant to be extended, it is never meant to be instantiated, we need to talk a little bit about some rules regarding the constructor. So in case of an abstract class, you can define a constructor in your abstract class, but it can never be called directly, because an abstract class, again, is never meant to be directly instantiated. In other words, you will never call new on the data type of the abstract class. If you would want to define a constructor, the class that is extending the abstract class, the subclass, would need to call the constructor for you. So that's one of the things that's important. We can't directly call constructor in an abstract class. It must be done through one of the subclasses. Another thing that's unique to an abstract class that is not normal in a normal class is that we can have what are called abstract methods. And abstract methods are methods that have no implementation. And we remember that the implementation of a method is that part between curly brackets. So there's no need to have implemented methods. Well, where do those methods get implemented? They actually get implemented in the subclass. So we're going to be able to defer the definition of our method implementations to the class that is subclassing our abstract class. And one other thing to note about abstract methods is that any class that contains even a single abstract method is itself an abstract class, regardless of how it is defined. So even if you forget the abstract keyword when defining your class, public abstract class, you would then go ahead and accidentally put an abstract method in there, you have automatically made that class abstract. So whether you have the keyword at the class definition or you have the keyword abstract in front of a method, either place, it's enough to make your entire class an abstract class. What does this look like in UML? Well, what you'll notice here is we have a class called animal, and the one thing that you should notice is that the name of this class is actually in italics, and italics in UML indicate an abstract class. So if we come down a little bit, you'll notice that I have a regular instance variable, and what I'm doing is, defining a generic animal. All animals have weight. I'm going to store the weight as an instance variable in the double. So that's kind of nice. And notice this idea of an animal, like what is a generic animal? It's just, if we had to talk about, I'm not a biologist, but animals have certain characteristics. And I would say one of those characteristics is that they have weight. Okay, so let's go down and look at behaviors. Well, notice I've got a get weight and a set weight behavior, and these are nothing different than what we've seen in the past in terms of regular accessors and mutators. So these I can write, right? These are methods that will get and set the value of weight. But here's something that's a little unique. I have an eat method, and notice that eat is also in italics. Well, since this is an abstract class, eat indicates by being in italics that this is an abstract method. And what that means is the user will not define this method in animal. We will not have any code between curly brackets for this method. And what will happen is the definition of this method will be deferred to the cat class. Because guess what? Animal is a generic concept. It's an abstraction of a concept. Okay? A cat, the subclass here in this case that is extending animal, is the concrete example of an animal that we want to use in our code. So notice that by inheriting from the animal class, the cat class automatically gets the get weight and set weight methods. It also gets the weight instance variable. And what's being told in this process is that the cat class needs to conform to the contract set up by the abstract animal class. In other words, because eat is an abstract class, cat, being the fact that it's not going to be an abstract class, it's a class we want to instantiate, we actually want to make cat objects, we'll need to actually implement the eat method. So you can think of it as the fact that every animal eats, but animals tend to eat in different ways. Like a cat might eat different than a dog, a cat probably definitely eats different than a bird, or a snake, or something along those lines. They're all animals, but they have different ways to eat. So it lets you say, look, I know that all animals eat, but I'm going to leave the implementation of how they eat up to you when you subclass the animal class, because I don't know exactly what type of animal you're going to create, and I know that animals can eat differently. So let's define this as an abstract method and leave or defer the implementation of that method to later. What's a good visualization of this? Well, I mean, has anyone ever seen a generic animal? It would be some frightening genetic mishap, possibly. But we all know what a cat looks like. But, so animal is a concept. Cat is an actualization. So I would probably imagine that a generic animal would look something like Meatwad from Aqua Teen Hunger Force, right? I mean, some really, really scary, like kind of moldable, shapeable being that really doesn't conform to any concept of an animal. So this is our generic animal up here. Cat is a class that extends animal. So when we go ahead and we extend the abstract class animal to form a cat, we're basically taking this generalization called animal, and we're turning it into a concrete representation of a type of animal. So again, we've got this abstract concept of animal, and then when we subclass it, we get all of those kind of abstract behaviors and properties that an animal should have, but then we can build on them to shape and make a concrete example of what an animal is, and in this case, cat. How does this differ from an interface? Well, an interface is a completely abstract class that defines a protocol for object interactions. So in our previous example, you'll notice that I've got, in my animal class, I have a mix of abstract and non-abstract methods, and I've got regular instance variables in that class. And abstract classes, really the only difference between an abstract class and a regular class is that we can't instantiate the class and that we can have these kind of undefined methods that we call abstract methods in them. But an interface is unique in that it can only contain abstract methods and a few other things. So let's run through this just like we did with the previous example. So interfaces may contain only static final variables. Well, that's unique, right? No instance variables. Why? Well, interfaces are not meant to be instantiated directly. There will be no instances of a specific interface data type, only implementing data types. And we'll talk a little more about those ramifications as we progress through the class. But an interface may only define static final variables, and that's an important thing to keep in your mind when you're defining interfaces. Interfaces may also only contain abstract methods, so you may only define methods without implementations in an interface. A couple other things is that interfaces cannot contain a constructor, because again, they're not meant to be instantiated. They're meant to be implemented by other classes, which would assumably have their own constructor. One of the cool things about interfaces is that they can extend other interfaces. So we're used to having this inheritance hierarchy of classes. When we utilize inheritance, we can also have interfaces that inherit from other interfaces. So you can kind of even abstract out general concepts in terms of interfaces and have like this whole set of really nicely defined hierarchies of protocols that people can implement at whatever level they deem appropriate. A couple things that are really nice. We know that this fact that in terms of inheritance, that classes can only extend one class. In other words, each child class or subclass can only have a single parent class because of single inheritance in Java. But classes can implement any number of interfaces that they want, up to whatever hard limit Java has. I would not want to implement more than a couple of interfaces on object because that would just be annoying, but I'm sure there's a limit around 255, or I have no idea what the implementation limit is for interfaces, but feel free to figure that one out on your own. But what's really nice here is that I can implement as many interfaces as I need. And this is one way that people often say that Java gets around this idea of single inheritance, because one of the things that happens is when you implement an interface, you are that data type. In other words, a class that implements an interface has an is a relationship with that interface. And so normally we can usually say that something like a cat is an animal. Well, a cat in that case really is only two data types. It is a cat and it is an animal. But if I went ahead and implemented an interface like pet, well, now my cat could be a pet, my cat could be a cat, and my cat can be an animal. So I can have a number of data types, or in other words, my object can be more polymorphic by implementing interfaces, because when you implement an interface, you are that given data type. Just like when you inherit from a parent class, you are that given data type. What's this look like in UML? Well, if we go up to the top, you're going to see guillemets, which are these less than signs and greater than signs, and the word interface. And basically what this does is it indicates that this block is an interface, and it gives the name of the interface, in this case a variable. So anyone implementing this interface would be of data type valuable. So we could say like, hey, gold is valuable. Yeah, because this interface is being implemented by this concrete class gold. Notice that in this case it defines or allows me to define behaviors. And basically what I'm saying here is if you comply to my valuable interface, then your class must have a method called isValuable, and it must return a Boolean. What happens inside of that method? I don't care. I don't know. All I'm saying is someone who wants to work with a selection of valuable objects should know that there is a method called isValuable there, and it should return a Boolean. And notice here that we have this interface defined. Notice that in Argo it throws in what's called a realization mark here, basically because when you implement an interface, it's said to be that you are realizing that interface. So in this case, gold implements the valuable interface. It's realizing that interface by agreeing to conform to the contract. And anytime you decide to conform to an interface, you are basically saying that yes, I will follow your rules, because if you don't, you'll get compiler errors. So in this case, gold is valuable, gold is gold, and gold will have a method called isValuable. So one of the things to note in UML is the difference here. Notice that when we do inheritance, we have a solid line. When we do realization of interfaces, we have a dashed line. So that's the only real difference in terms of UML in the case of those items. So here's some key takeaways. Abstract classes and interfaces allow us to define a set of standard protocols for programmers to implement in their code. So what's really great here that a lot of, I think, students don't quite get is that and I made some comments about this on the course, is that you can all agree to name methods certain things, and you can, everyone on your software team or around the world can agree to have methods named a certain thing that returns a certain value. But the reality is people are going to, they like to do their own thing, or they get tired, or they get lazy. One of the cool things about abstract classes and interfaces is it allows you to define in code a set standard or a set way for people to code to that guarantees through the compiler that if you are, say, a valuable object, you implement the interface valuable, the compiler will guarantee that your method has an isValuable method. And that's so much more powerful than just having someone proofread it or just a handshake agreement around a table. So this idea that having standardization in code is excellent, but having the compiler enforce that standardization is amazing because it allows for a lot more power. So when we define abstract classes and we define interfaces, what we're really doing is not only are we allowing flexibility into our code, but we are defining a standard way of doing things for other programmers who work with our code. And once you have standard ways of doing things, then people can build on top of those standards with your code and do some really powerful things because they can expect that your code works a specific ways. Interfaces also allow objects to be polymorphic. I just said that beyond the constraints of single inheritance. Again, if you implement an interface, you have an is-a relationship with that interface, so you are a type of that data. And also one of the things that I often tell students to keep in mind is that for every interface that you define, someone has to code all of the implementations for all of those methods. So as we start thinking more and more about OO design, you don't want to see interfaces as kind of this end-all solution, because for every time you implement an interface, you have to write all the implementations for all of its methods, and that gets to be a lot of work. And as we get into talking about design patterns, and we get into talking more in depth about OO design, we'll look at some ways to reduce the need to rewrite many methods over and over and over and over again because you have implemented interfaces. Let's take a look at some of the samples discussed in the concepts section of this lecture and how they translate to code. Sitting in front of me is some code that represents a class that represents an animal. And what we look here is that we've got public abstract class animal. The only difference in the definition of this class is the abstract keyword. And we know that abstract classes, by their definition, cannot be instantiated. So the compiler is going to enforce that. So if I go over to my driver here and move that up so we can see both, I'm trying to instantiate an instance of the animal class. I'm going to compile that, and what's going to happen is you're going to notice that I get an error. Well, that is because animal is declared as abstract and it cannot be instantiated. So there's proof that we cannot instantiate abstract classes. And that makes sense, right? Because we don't want we don't want the concept of an animal to exist within our code. We only want a specific type of animal to exist. So I have a class, and it is called cat. And cat extends animal. So notice that animal is an abstract class, cat is extending that class, and now I can go ahead and if I change what I'm trying to instantiate here to cat, will be fine in terms of compilation. Because I can instantiate an object that is not abstract, even though it extends that abstract class. Why? Because I'm saying, okay, here's this general concept of animal. What I would like to do is make a specific example of that animal. So the semantics play a large role in this, and abstract classes allow us to control those specific semantics. So in an abstract class, I can define, variables just like I would normally. So we'll do private double weight, and I'm not going to go ahead and, let's do like a getter, right? So public double get weight, and there's a full method, right? And I can return weight, and if I wanted to, I could, in my driver, say something along the lines of a.get weight, and we would see that represented in our class. And we get no errors, and obviously that's not doing anything, it's not printing anything, but the key here is that we're not seeing any errors upon compilation. And even if I run it, right, nothing's going to happen. But again, we're getting no runtime errors, we're getting no compile errors, so we know that that's cool. And that means we know that the cat class is inheriting this method. But one of the other things we can do is have abstract methods inside of our abstract classes. So I'm going to do public abstract void eat. Now, the big difference between this method and the previous method is that this method has no implementation. And instead of having a set of curly brackets that have a block of code inside of them, abstract methods have a simple semicolon at the end and the abstract keyword to indicate that, hey, this is a method that has no implementation and it's abstract. And that means that I'm deferring the implementation of this method to my child class. So I can compile that. And you can see that my class compiles fine because it's abstract. And if I come over to my driver, I'm going to go ahead and I'm going to compile. And I'm going to run. And I didn't get an error. Let's come over here, compile this. There we go. That was interesting that I didn't get the error from the other class. But anyway, not going to dig into why that happened, but I'll leave that in the lecture because that was kind of an interesting thing to happen. I'm not sure what happened there. Anyway, notice that when I try to compile my cat class, I'm getting an error. I'm getting cat extends animal, but it's not abstract, and it does not override the abstract method eat. So here's the thing. Whenever you choose to extend an abstract class, if there are any abstract methods in that class, then you as the programmer must implement those abstract methods. It's a contract. So the person who set up the animal class, me, has said that, look, anyone who extends this class must either implement the abstract class eat or themselves be abstract. So I can get rid of that method by making cat abstract, which although isn't really what I want to do. Right, so I can hit compile, and notice now that error goes away, but I want people to be able to actually make cats. So I can, so I'm not going to really want to do that. So how do I make this happy? Well, I need to go ahead and I need to implement the eat method. And all I'm going to do is put a little print statement in here, and something like grr. And now I can compile this, and I'm good. Notice that cat is not abstract. Notice that it gives me no errors. And if I come over to my driver, I'll change this to eat. Compile, run, and I get grr. So what I've been able to do here is defer the definition of this method to the cat class. In other words, tell any classes that extend from me to go ahead and implement eat. So what's really nice is we get this mix of having pre-written code and code that we can just inherit and use right off the bat, so that's nice. There's a reusability factor there. And what also is nice is that we have this idea of abstract methods that say, well, not every animal eats the same, or not every animal speaks the same. So I'm going to let whoever extends me write those methods. But what I'm going to do is I'm going to define these methods here anyway, so that I can guarantee that everything that extends animal, or everything that is an animal, has a common name or a common method signature for how it goes about performing these actions. And that's really, really important. Now let's go ahead and look at how this relates to interfaces. In this class, I've defined an interface called valuable. And we talked about this interface before. Now, the difference between interfaces and abstract classes is that interfaces can only contain abstract classes. Okay? Interfaces can only contain abstract methods. So I can go ahead, public abstract is valuable. And now I've got an abstract class. Notice, by the way, I can compile that. We should be good. Oh, helps if I have Boolean in there. I need a return type. So now I get compilation and it works fine. And I can make this bigger so you can see there were no errors. Notice, by the way, that because an interface can only contain abstract methods, you can just leave the abstract keyword off, because the compiler just knows, hey, this is an interface. I know any method signature I see in here is going to be abstract. So I can get rid of the keyword and I'm still fine. So if you like seeing it, leave it in. If you don't, take it out. It doesn't really harm anything. But what happens if, for example, I have something like, I actually put a method in here. I call it like going to error, and I actually have a real method in here. I'll just like return true. So now what happens when I compile this? Well, I get an error because it says interface methods cannot have a body, right? The body being that segment between the curly brackets. So it's really trying to say, hey, look, if you're going to go ahead and you're going to put method definitions into an interface, they have to be abstract. In other words, they cannot have an implementation. They cannot have a body. They cannot have the component between the curly brackets. So there's my interface. It's compiling. We know it's good. So now I'm going to go over to my class called gold. And what I'm going to do is I'm going to implement valuable. So now you'll see that my class is going to implement the valuable class. And implements is the keyword for interfaces in Java. So I go ahead and compile it. It says, yo, gold is not abstract and does not override abstract method is valuable. So we get the same error basically that we got before. It's saying, hey, look, you agreed to implement this interface. And by agreeing to implement that interface, you must provide an implementation or definition for every method that that interface provides. So let's go ahead and do it. Oops. Public Boolean is valuable. Let's make this so we can see what we're doing here. Get some spaces in there so it's readable. And all I'm going to do is just put return true because it's gold, right? I don't need anything beyond that. Now when I compile this, it compiles. There's really nothing to run, right? Because I haven't created anything. So what's interesting here is that we note that when we have an interface and we implement the interface, then just like in an abstract class, we're required to implement all of the abstract methods in that class. And again, the implements keyword is what allows us to indicate that we want to implement a specific interface. By the way, if we had multiple interfaces that we wanted to implement, you just separate them with a comma after the implements keyword. So let's say, for example, I want gold to implement valuable and comparable. All I have to do is go ahead and put a comma between each of the interfaces that I wish to implement, up to whatever the limit is on interfaces being implemented in Java. So that's the basics of using interfaces and of using abstract classes. And again, these are some more design tools that we have available to us. One thing if we wanted to take a look at in the driver, I guess before we exit, is note that cat can actually be stored in an animal variable because cat is polymorphic, right? A cat is an animal. So if I go ahead and I run this, compile it, right? No errors. Pull this up so we can kind of see everything in the window. I use this skinny window so that the code doesn't get fuzzy when I compress the videos, so it's a little bit of an odd size to work with. And let's run it. And it works. It still works. Why? Because animal, cat is a subclass of animal, so it's a specialization of my abstract class, and the animal reference knows about the eat method. Why? Because the animal reference actually went ahead and defined that interface for eat. So I could actually write like a zoo application that would have many animals, and I could just store them all into an array that stores animal components and just call the eat method on them. We have the same ability to do this with gold. Because gold is of type valuable. Remember, when you implement an interface, then you are an item of that data. So this object is type gold, it is type valuable. Okay, so we have this idea of polymorphism, and we can really leverage that using interfaces, using inheritance, using abstract classes, and building and designing our classes in such a ways that are appropriate, right? There's that word in OO design again, for the task at hand.